Gentlemen, welcome to topic 6 in maths this year, which is networks. So what is a network? Well, a network is a set of connections between people or destinations or activities. What you will see is plenty of these type of diagrams that have got some lines with some dots and also some letters next to them. Now, what do they represent, you might ask? Well, each of those points there in orange we call vertices, okay, or one vertex. Okay, and the lines that join these points are called edges, and you can see them marked in yellow. All right, a degree of vertex is the number of edges that come off each of the vertices. So if we were to take D, for example, all right, now there is 1, 2, 3 lines coming off D. So the degree of vertex D would be 3. Now, if we were to take into account maybe B, all right, you'd have to again count how many come off there. So there's 1, 2, 3, 4, 5. The degree of vertex B would be 5. Multiple edges, well, these exist when two vertices are connected by more than one edge. So if we take vertex A and B together, there and there, they're actually connected by 2 edges. So we call that and we say that that has multiple edges. Loop. Now, you might have just seen that come up there. There wasn't actually a loop in this network. However, I've drawn one there which is in black around the vertex D. A loop connects to itself. Okay, so a loop connects to itself, and you'll see a few more of them throughout this topic. One thing to remember or to know with a loop is that it counts as one edge, so there's one line, but it actually counts as 2 degrees because there are 2 connections. So if we take into account D now, there was 3, but now there's 2 more edges that are off that, also 2 more degrees, I should say. So now the degree would be 5 for D. Moving on. A simple graph is a graph with no multiple edges or loops. So you can see up here, this is a simple graph, and the one on the right is not a simple graph because you can see that there are multiple edges connecting the two. An isolated vertex, not joined by any edges. And I think it's pretty obvious in this graph that edge, the vertex J, is an isolated vertex. Now, a degenerate graph has all vertices isolated. Okay, so there's no edges whatsoever in a degenerative graph. A connected graph is when each vertex can be reached from any other vertex. Okay, so the one on the left there, obviously that's connected because you can start and just follow each of the edges around and get to them all. However, the one on the right, you actually can't get to those 2 in the middle. There's no way of getting there because there's no edge connecting them. And finally, a complete graph is a simple graph that has every vertex connected to every other vertex. Okay, so you can see in the one on the left, a very simple graph with 3 vertices, and the one on the right, it's got 5 vertices. You can see there's much more or many more lines in there. So you can imagine if there was maybe 7 vertices or 9 vertices or maybe 20 vertices, there would be just a plethora of lines and edges connecting them. Okay, so that's where all of them can be reached from all different ones. Now, getting into some examples. So we're going to use this network and we're going to find out a few things. So what is the number of edges on this? If you've taken some time, we'll actually answer each of these questions. Find the number of vertices, find the degree of each vertex, and we're going to confirm that this rule applies for this network. So what is the number of edges? Well, we can just simply draw on here and count them. There's 1, 2, 3, 4, 5, 6, 7. Number of edges would be 7. Find the number of vertices. Well, the vertices are, again, they're our dots, aren't they? So we can go 1, 2, 3, 4, 5. Find the degree of each vertex. Now, this is a little bit more complex because we actually have to go to each vertex and count how many degrees are off each. So let's just have a go. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. 1, 2, and remember a loop counts as 2 degrees, so that would be 4 as well. And obviously A, there are no edges coming off there, so there's no degrees to that. Now, if we actually total all of them up, because we're going to need to do that to confirm this rule, there would be 3, 6, 10, 14 is the sum of all of the vertex degrees. All right, and this rule is saying that we need to confirm that the number of edges equals this. 14 divided by 2 is obviously 7. Are there 7 edges? Well, yes, there is. So we can confirm that this is correct for this. Here, we've got another little formula, and this one is for a complete graph. Now, a complete graph, you'll recall, is a network that has all of the vertices connected by all of the edges. So you can access any vertice from any of the other vertices. Now, the formula that we use is number of edges equals n, bracket n minus 1, close bracket over 2. Remembering that n, in this case, would be the number of vertices. Now, we can answer a number of questions for this. In this case, we are asked how many edges does a complete graph on 15 vertices have? We could put this into solve, but the workings out would obviously be, well, the number of edges is what we're trying to work out. N would be 15. 15 minus 1 over 2. And you will have worked out in your calculator that the answer is 105. So there would be 105 edges that connect a graph with a complete graph, that is, with 15 vertices. Now, to put things into perspective, what that might look like, it might look like something like this. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And all of these would be connected to each other. So this vertex would be connected to all of them. You can start to see why there are so many edges. All right, then you go to this, and that would be connected to all of them. Okay, so obviously there would be a lot of edges. In fact, there'd be 105 edges on a graph like this. Last part here of the first video is matrix representation. A graph can be represented by a table or an adjacency matrix in which the numbers denote how many edges connect each pair of vertices. Okay, so we're going to compare the graph below and its associated adjacency matrix. So reading this through, we could start by saying that, let's obviously start at AA. Well, is A connected to A, and how many times? Well, it's connected once there, and then we also go back and go once there. So we could call that 2, and that's obviously a loop. So a loop would be represented by 2 in an adjacency matrix. A to B. How many times can you get from A to B? Well, you can go in that top one there and that bottom one. So that results in 2 as well. Sorry, my pen just stopped working. 2. So A to B would be 2. A to C, we can get there once. A to D, well, we can't get there via any of the edges. Then we go to this next one. How many times can we get from B to A? 1, 2. B to B, well, B's not connected by a loop, so that's a 0. B to C, that's 1. And B cannot get to D. If you go to C, C can get to A and it can get to B. A, B, but it can't get to anything else. And D, well, obviously that's isolated, so it can't get to anything. And that's what a matrix representation looks like for this particular example. Now, if we were to create it the other way around, we could be able to go through this. So we could just start using A. A can get to C, and it can get to C twice. So we'd put a 2 in there. All right, let's look at B. B gets to itself. And remember, a loop is represented by 2 because it can go 2 ways. It could go on that way as well. B can also get to C, and it can get to D. So there's 1 there and there's 1 there. Let's look at C. Well, C can go to A twice. It can go to B. It can go to D. Can it go to itself? Well, no, there's no loop in there. And obviously it can't get straight to itself. Can it get to E? No, it can't. Let's look at D. D can get to B, it can get to C, and it can get to E. B, C, and E. And then if we look at E, well, E can get to D, and it can get to itself, not just twice, but we call that 4 times because it's got a double loop there. And then all we do is fill in the gaps with zeros. And this again would be our matrix representation for this particular example.